Okay, so I think we're good. We're at like over 50%. I think what 165. That's pretty good. I think that's good enough time to start. So, couple of things. One, sorry, I had to get another due. So one is since there was some technical difficulties getting all this set up, um, but now it seems to be working fine. So yeah, I mean, I'm assuming everybody can hear me. I didn't have issues with my last couple lectures, but I'd had some audio issues earlier. I just wanted to make sure everything was okay. Um, so anyway, basically, as I said in my announcements, gonna be pretty flexible. If it turns out that I think it would be more use to you to record the lectures um, at some other time, so not live stream the lectures, and then instead of lecturing, hold like problem sessions, I may do that instead. Um, so, so if it turns out that that's, I think that would work out better, then that's what I'll do. For now, I'm going to lecture like I would lecture if I was going to be at a blackboard. So we'll see how this is going to go. One thing is that I may be recording some lectures just to kind of catch us up, but I'm not going to like toss like a giant pile of lectures on you and then say, oh, go through these lectures and then do something on those lectures like next week, right? I'm not going to do that. So I will, this is I'm going to lessen the burden on you guys as much as possible. Um, so anyway, um, um, so whatever happens, basically the main thing is that the burden on you all will be kept to a minimum. So I'm not gonna whatever I end up deciding, it's not gonna be something uh, that makes the course load like worse for you really. Okay. So anyway, um, so the way that this is gonna work is for now anyway. Like I said, as I'm just gonna live stream the lectures. If it like I said, if it turns out that it I think it'd be better, or you'd be better served by me hosting problem sessions instead and recording the lecture some other time, then that's what I'll do. But anyway, so we'll see how it goes. So a couple of things first. I mentioned in the announcements that the discussion sections with your TAs, those will happen via Zoom. Your TAs will take care of that, so they will send out Zoom invites um, for each of their sections. Those will be held, so I will know over the weekend when I'm going to have those being held. So they won't be held at the usual time. You're not going to have to get up at 8 a.m. On a Wednesday in order to do this. But oh, what is this? What's going on? Oh, I see. What can I do here? Uh, let us see here. There we go. 300 seconds. That's not long enough. Anyway, okay. So, all right. So anyway, yeah, maybe I'll get one of my friends that's bored. Maybe I'll get them to be a moderator for chat. Anyway, so the way that so the way that this is going to go is regardless of how the lectures are going to go down, this is going to be uploaded to YouTube after it's over. So it will be automatically added since I have it set as public. It should be automatically added pretty much immediately. If not, it'll take a couple hours for it to be uploaded. So everything that gets done, whether the lectures are recorded, not when I'm live streaming. So if I record lectures outside of this and put them up, regardless of how it gets done, everything will be recorded. You're not going to be required to like there's not going to be anything that's time sensitive in that you have to like show up to lecture and I'm going to give you a quiz and have you. That's not going to happen. So nothing is time sensitive like that. So maybe I should go over those important things first. So one thing is the assignments that you have left. So you were going to have 2 midterms. That's not going to happen now. You're going to have 1 midterm and 1 final. So um, so your 1 midterm is going to be it'll be in a few weeks, like 3-ish weeks. So maybe like after the 3rd week of April, you're going to have a midterm that is focused on all the material we've covered um, up through or from the first exam until we have the test. So I hope to have that end at uh, at Laplace transforms is probably where that will end. So basically your second midterm will be on all of the chapter 2 stuff in the online notes. And then in the remaining course time, I'll go over the stuff in chapter 3, which is linear systems. And then you'll have a final exam, which will cover everything. So it'll be comprehensive. And the way that it'll go is basically when your midterm is scheduled, I will post the midterm to Elms. So I'll let everyone know when it's going to happen, and I will post it to Elms and send out an announcement that it's posted. You'll have like 2 to 3 days to work on it. So you can't work with other people. It's just you. So you work on your exam and you hand it in. You turn it in, and that turning in, it'll either be via Elms or at your TA's discretion, emailing them a copy. However we're going to do that. Probably just going to turn it into Elms. So you're going to have a midterm in that format, and you're going to have the final exam also be in that format. So those are the 2 main assignments you have left that haven't been graded, or that are going to contribute to your final grade. The others are MATLAB projects. You're going to have like 1 to 2-ish more MATLAB projects. Those are going to be of the exact same form. You can work in groups on those. In fact, you need to work in groups with people on those, kind of just like before, and you will submit them. Only one group needs to submit. Same thing, you'll submit them via Elms, or emailing the published PDF to your TA, however they want it. So the MATLABs and the midterm and the final, that's going to determine the rest of your grade. Quizzes, basically, as you saw in the announcement, I altered the weighting of the quizzes. Basically, you've taken something like 5 or 6 quizzes. I'm going to drop one of those. I'm going to drop your lowest quiz from those that you took. Any of the remaining quizzes that I give to you as quizzes, or your TAs give to you as quizzes, they're not going to be graded. It's just purely for you, for your benefit. Let me see some other timestamped. Yeah, I mean, the plan is if I end up sticking with the lecture format, then I will try to timestamp the examples in the lecture. If I end up switching to recording the lectures and then holding like problem sessions, then I'm not going to timestamp stuff unless I think like a particular example is good. Then I'll timestamp it. But other than that, yeah. So I do plan on adding some timestamps though. Someone's asking about the exam. Well, I mean, the exam is timed in the sense that I'm going to give it to you, and then you're going to have like 2 to 3 days to do it, and I'll say it's due, 3 days from like, or I'll say it's due at like midnight on some day. But no, it's not timed in any way. Like I'm not going to say like, you open this in your browser, then you have an hour, right? It's nothing like that. You're going to have like days to work on it. Yeah, I'm dropping 1 quiz. Let's see. Extended time work. Any ADS students can email me if there's concerns about that. So the thing is that it's not even though I'm giving you 3 days to do it, it's not a 3-day long exam. It's an exam that, in terms of absolute length, is not really much longer than an in-class exam. So there shouldn't be any kind of time issues with this exam. Yeah. I don't. I think I answered everything else. Yeah, I think so. Okay. Um, all right. So, that covers everything. And like I said, these everything will be posted. So if you missed something or if you weren't paying attention or whatever, you can always go back and watch it later. Okay. So, I think that's pretty much all I wanted to cover as far as the admin stuff. I will let you guys know. Oh wait. Oh man, my browser is not liking this. Okay, we're good. We're not crashing. That's good. Um, yeah, well, I mean, if you can tell me how Zoom would work for a class of like 289 students, then I've never used Zoom. I mean, I've also I've never streamed anything on YouTube either, but I thought this would work out a lot better. Will there be online math success? I'm not totally sure. I know that there's been some posting that I haven't read everything, but I'm not totally sure how they're doing that. I know the GSS sessions are going to continue as normal, and Caitlin and Lauren, I think, have already sent out some messages about that. Anyway, so uh, anything else? I think that's pretty much everything for the admin stuff. Main thing that I wanted to get across though is that yeah, I will be totally. So I already basically posted the revamped syllabus, but I'll be straightening all that stuff out and making it look a lot nicer, and including I think on the syllabus page on Elms I will start linking all of the videos in order, but also if you just want to look at the videos, I'm going to put them all on this account. I'm going to label them all Math 246. So this is online lecture 1. I'm just going to label them in order, and in the description I'm going to say what I cover and eventually get around to timestamping stuff. So that's the idea. So anyway, um, but I don't. Uh, I think that's all I wanted to say. Okay. So, key identity stuff. I know that I'd started on this stuff right before we were done for the rest of the semester. So, I wanted to do a couple more examples of key identity stuff. Hopefully enough that uh, that I can record. I think over the weekend I'll record a lecture on undetermined coefficients. So I won't live stream that, I'll just record it. And then we'll move on to, after that, we'll move on to variation of parameters. But I wanted to at least do one of the methods live stream since I didn't get a chance. I canceled that last Thursday's class. So um, anyway, okay, so key identity stuff. And let me know. And like sometimes I'll get busy writing stuff. So if I've accidentally pushed the paper up off the camera, then let me know, and I'll fix it. Um, we have another lecture this week, not a live streamed one. I'm gonna record something and put it up over the weekend. Unfortunately, I wasn't able to get this working in time. They actually just shipped these document cameras to us a few days ago, and I couldn't. It was a real hassle trying to get all this to work with my computing needs are very niche, and so like even though technically my computers were perfectly fine doing all this, they're set up in such a way that it was actually really hard getting it to work. But anyway, so it seems like it's working now. Okay, so like I said, I'll periodically be going back and forth between tabs here, so if I don't answer questions for a bit, that's why, because I'm looking at something else. Okay, so just to remind you of the idea. So the idea is that for these constant coefficient non-homogeneous problems, the problem looks something like this. So you have L of y is equal to f of t, right? So we know how to do the homogeneous case where this right-hand side function is 0. But the question is, what do I do when this is just some function f of t instead? So this first method that I'm going to talk about is key identities. And so I've already, like I said, I already done a couple of examples of this, but just to remind you how this goes. The idea is that like the main key identity, or if you want to call it like the key identity, is the following. So first of all, it's noting, remember L is the operator. It's the differential operator that tells you what the left-hand side of the differential equation looks like. So what are the key identities? First of all, there's some quantities related to F that I have to write out. So this F is in characteristic form. So I'm not going to write out because it would take too long to do it, and I wrote it out in complete exhaustion the last couple of lectures we had. So what it means if the right-hand side is in characteristic form is that basically it's a particular combination of polynomials times exponential times cosine and sine functions, right? So that's what it means. But remember, associated to a right-hand side function in characteristic form were a couple of quantities. So there was d was the degree, and that was the degree of the highest degree polynomial that made up f, right? So you had some polynomial pieces multiplying the exponential and sine and cosine bits. And the largest degree showing up is the degree of f. And remember, this f is not always a polynomial, so that's why it's technically degree. That's just what we're calling it. And then the other thing is there's characteristic. So mu plus, or it's written as mu plus I nu. So this is the characteristic. Okay. And the characteristic was, let's see, am I going to be able to avoid? Okay. So I guess I will write this out. So what are these things? So both of these things, the important thing to remember is that both of these things can be read off just by looking at f. Completely ignoring the left-hand side, just looking at f, you can read off both these quantities. So if a function f is in characteristic form, what that means is that f looks like this. It is some polynomial. We'll call it a sub. I think I did it this way. I think before I said this is like a sub d t to the d plus a sub d minus 1 t to the d minus 1 and so on, all the way out to a1 t plus a naught times e to the mu t cosine of nu t plus some potentially different polynomial. What am I doing? There we go. E to the mu t sine nu t, right? So this is what it means for one of these things to be in characteristic form. This is done, let me look this up real quick. This is done on this is page 2 of section 2.6. So page 2, section 2.6 is where this is outlined. It's at the bottom of page 2, right after degree, characteristic, multiplicity. Okay, all right, so now we remember that. Okay, so then degree and characteristic can be read off just from looking at f. Okay, so you look at f, you can read off degree and characteristic. But there's another quantity that you have to know before you can start any of this process, and that's the multiplicity. And the multiplicity cannot be read just by looking at f. The multiplicity can only be determined when you look at f, and then you look at the left-hand side to answer a specific question. And the question is whether or not this characteristic is actually a root of the characteristic polynomial associated to L. Okay, so P of Z is the characteristic polynomial associated to L. Okay, and so there's another quantity, M, which is multiplicity. So remember, the multiplicity, M, is the multiplicity of this number, the characteristic of f, as a root of the characteristic polynomial of L. So what that means is that I look at the characteristic here. I ask myself, is this characteristic a root of the characteristic polynomial, okay, of the left-hand side? If it is not, the multiplicity is 0. If it is, then I say, okay, it's a root. Is it a simple root? That means multiplicity 1. Or is it some repeated root, right? So if it's a repeated root, then I say, what is its multiplicity as a root, the characteristic polynomial? And that's what m is. If it's a simple root, then m is 1. Okay, and that's how this works. And you have to know all three of these things before you can even start, okay, the process. Because how does the process go? So this is done on page 6 of 2.6. So there are key identities that I have to write out. So there's the key identity, which I hinted at earlier, which is L of e to the zt is p of z e to the z of t. Okay. And then there is a list. This is the first key identity, or I guess with the way that it's numbered in the textbook, this is the 0th key identity. So if you like, this is the 0th key identity. And so the first key identity is the derivative of this, and you'll see, actually I already showed you in class. I probably wasted too much lecture time doing that calculation in class. So L of t e to the zt is p of z t e to the z t plus p prime of z e to the zt. Okay, and then the second, if you like, is L of t squared e to the zt, and this is equal to p of z t squared e to the zt plus 2 p prime z t e to the zt plus p double prime of z e to the zt. I'm going to write one more, and then I'm going to remind you what the pattern was that we saw in lecture. So one more, L of t cubed e to the zt was p of z t cubed e to the zt plus 3 p prime z t squared e to the zt plus 3 p double prime z t e to the zt plus p triple prime. I'm almost getting off camera here. P triple prime of z e to the zt. Okay, there we go. All right, and of course there's no end to this. This list continues. So the question is, where does this pattern come from? So you might remember that we noticed in class, like, oh, well, I can determine as many of these as I want if I notice that pattern just by looking at the coefficients. And the coefficients, of course, are determined by Pascal's triangle. So this follows exactly. If I wanted to know the next one, there's my coefficients, and this continues in that way. Okay, so so I can come up with as many of those that list of key identities as I need to. Okay, so the question is, again, why do we use that? Why do we care about that at all? That list is going to be what we use to do this process. So before I start, let me look and see if there's any questions. Nope, I think we're good. Okay, all right. So anyway, so how does this go? So here's the process. So again, I know that I already did all this in lecture. I just wanted to do it again because it's been a while. So I'll do this again, then we'll do a bunch of examples. Okay, so first is write down key identity. The way that we do this is determined by those quantities I mentioned at the beginning. So before I even start this process, I have to know a couple of things. Oh, that glare is probably annoying. So before I even start this process, I have to know a couple of quantities. So I have to know m, d, and mu plus I nu. Now it turns out that this mu plus I nu, since it is used to determine m, what I really need to know is d and m. This is like a secondary thing, but I need to know all of these. Okay, there's no getting around it. But m and d is going to determine this process, and you'll see how that is. So one, I write down the key identity through its m plus d derivative. Okay, and that's the derivative with respect to z. Um, and going back, let me bring this back. So we saw in lecture that we can view each of these things as being a derivative, okay, with respect to z of this whole thing. So in fact, we showed the first step in lecture. I showed that these are related by being the derivative of the other. So that's what it means. I have this starting key identity, and then these are first derivative, second derivative, third derivative, and so on of these things. Okay. So that's what I mean there. So you would start at multiplicity m and go through m plus d. So maybe I should say that. So writing down the key identity, starting at m, we'll see what that means, and go through its m plus d derivative. What this means is that if the degree is 0, I go starting at the mth key identity through its m plus d derivative. If d is 0, I start at m and I end at m. And so in that entire list, going back, in this entire list, I would only need one of the equations. Okay. For a completely general problem, I need m through m plus d. So if m is 0 and d is 2, I would need this starting equation, its first derivative, and its second derivative. I would need all three of those equations. And I will show you in the examples of what it means when I say I need them, okay, because I will need some linear combination of those things to make everything work out okay. All right, that's the idea. But if the degree is 0, I only need a single one of these equations. Not necessarily the first one. Maybe I have multiplicity that's 2, so I start here instead. Okay. So the point is that the degree is the thing that tells you how many of those equations you might need to use. Okay, so that's the first step in the process. Then next, I evaluate the mth through the m plus dth derivatives. So the textbook says that it doesn't say this starting at m bit, but here it says I'm only evaluating the ones m through m plus d. So that's what it means. That's why I said in this first step you actually don't need the full list. You only need to know from m to m plus d. Okay, so anyway, so I evaluate the m through the m plus d derivatives of the key identity at the characteristic by setting by setting z equal to mu plus I nu. Okay. All right, and so lastly, this is where what I said earlier about using everything in this list, so from m to m plus d, comes in. So I want to find a linear combination of the resulting d plus 1 equations. Whose right-hand side has real part equal to f of t. And of course the point is this lets me read off the particular solution. So remember, I harped on this for a while before our break. The idea in solving a non-homogeneous problem boils down entirely to finding a particular solution. The reason for that is that in general, remember, you have an equation that looks like this, okay? When you have an equation that looks like this, the general equation to this thing always looks like the following. It is the homogeneous solution. What does that mean? This is the solution to the associated homogeneous equation L of y is equal to 0, okay, plus particular solution. Okay, so we spent a little bit of time finding this, right? This is the thing that you should be able to do in your sleep by now. So this is the solution to L y is equal to 0, and this is the particular solution. Now, again, I explained why it wasn't circular to say, oh, to find the general solution, I need to find a solution to L of y equals f of t. Because this is the general solution, whereas the particular solution is just any old solution. Okay, so my claim is that any solution to L of y equals f of t has to be in this form. Okay, homogeneous solution I know how to find. And as I said in class, unfortunately, that's like 5% of the problem. And 95% of the problem is finding this particular solution. And so the entire purpose of this key identities method is to find this particular solution. Okay, so I did a couple of examples in lecture. Let me skip ahead and try to pick one that maybe I didn't do. Okay, I'm pretty sure I did that one in class. I may have did this one as well, but I'm going to do it anyway just for practice. So let's see how this works. Okay, so here's an example. All right, so find a general solution to the following. Let's say y double prime minus 6y prime plus 9y is equal to 4 e to the 3t. I'm pretty sure I did this at the very end of some lecture. Let me see, are there any relevant things here? Let's see here. Seems okay. Seems okay. I mean, there's some, there's some spammers, but it's okay. All right, so anyway, so, oh man, browser really not liking it. Okay, continuing on. So, general solution to this. As I claimed before, general solution to any non-homogeneous constant coefficient equation like this comes in the following form. So general solution is, you can even make a habit of really enforcing this by writing it over and over and over again. Y of t is the homogeneous part plus particular solution. Okay, so finding this is no problem. I'll do that in a second. Finding this, we're going to use key identities for. Okay, so this is what my general solution looks like. I'll rewrite that in a second once I know what these things are. So first, homogeneous, associated homogeneous problem. So the associated homogeneous problem is y double prime minus 6y prime plus 9y is equal to 0. So how do I solve a homogeneous problem? I look at the characteristic polynomial. So characteristic polynomial is z squared minus 6z plus 9. Does that factor? It definitely does. So it factors as z minus 3 squared. And let's just check. Minus 3z is minus 6z. Minus 3 times minus 3 is 9. We're good. Okay, so this is how this thing factors. Okay, so this has a single real double root, right? So root, if you like, you can say the roots are 3 and 3. Okay, so you have a double root. How do you write out the homogeneous solution associated to double rooted characteristic polynomial? Well, it's easy. This is just, so this is c sub 1 e to the 3t plus c sub 2 t e to the 3t, right? This was the trick. Okay, so that's the homogeneous solution. All right, so that was straightforward. That's just a recipe I follow. So now I want to find particular solution. Before I can even start, I have to ask, what is this? Right? What is this? I have some non-homogeneous part. The right-hand side is some function of t. I need to know some quantities associated to this. So the first two things I should always write out are the things that don't even need me paying attention to this. So I look at it and I say, okay, what's the degree of this thing? Well, this thing does not involve any non-trivial polynomial of t. Right, what I mean by that is there's not even a t outside of this exponent. Right, so there's no polynomial part. If you go back to first page over here, so here is my function in characteristic form. So if it is going to have a degree that is non-zero, I have to have a t showing up here multiplying this e to the t cosine or e to the t sine term. Okay, so if I just have constants showing up there, then the degree is 0. Okay, but that's what I have going on here. So the degree here is 0. Okay, so degree is 0. Okay, what is the characteristic? So characteristic mu plus I nu is, again, bringing back my description. The characteristic mu plus I nu is determined by looking and seeing what this mu here is, the coefficient of t in the exponent, and what nu is this coefficient on the t and the cosine and sine terms. Well, the cosine and sine don't show up anywhere here, right? So nu is 0. Okay, so I only have one of these terms showing up, and then mu is 3. So mu plus I nu is actually 3. Okay, now I can't write what the multiplicity is yet. I have to consider what's going on here. Mu plus I nu is 3. Okay. Is 3 a root of the characteristic polynomial? It is. And its multiplicity as a root of the characteristic polynomial is 2. So what is the multiplicity of f? It's 2. Okay, so let me go back to my process here. What do I do? Okay, I write down the key identities through its m plus dth derivative. Well, d is 0 and m is 2. So my goal is I evaluate the second key identity through the second key identity since d is 0. So I only have to use a single thing in that list. In fact, I've already written out some of these key identities. So what is the thing that I'm going to be using here? Well, I'm going to be using this one in this case. Okay. So that's what I'm going to be using. Okay. So how does this work? So looking at this thing, I say, okay, I'm going to write that out. Let's just go ahead and write it out here. So L of t squared e to the zt is equal to p of z t squared e to the z of t plus 2 p prime z t e to the z of t plus p double prime of z e to the zt. Okay. All right. So, what do I do here? Well, I evaluate at mu plus I nu, but mu plus I nu is 3, right? So mu plus I nu is 3. So I evaluate these at 3. Okay, so then this is P of 3, and this is L of t squared e to the 3t. L of t squared e to the 3t is P of 3 t squared e to the 3 of t plus 2 times P prime of 3 t e to the 3 of t plus P double prime of 3 e to the 3t. Okay, let's think about this for a second. Okay, so P of z is z squared minus 6z plus 9. Okay, so then what is P prime of z? Well, I can figure out this without thinking too hard. This is 2z minus 6. And while we're at it, we need to compute P double prime. So P double prime of z is 2. Okay. So rewriting this, this is saying that L of t squared e to the 3t is P of 3 is what? Well, P of z is, well, z squared minus 6z plus 9, so it's z minus 3 squared. When I plug in 3 there, what do I get? I get 3 minus 3 squared. I get 0. You know that because it's a root of p, so of course you get 0 here. So this is 0 t squared e to the 3t plus 2 times p prime is 2z minus 6. So this is 2 times 3 minus 6. Hey, that's also going to be 0. T e to the 3t. So both of those are 0. Plus p double prime of 3 is 2, but p double prime of z is 2 regardless of what I'm plugging in there because it's constant. So this is 2e to the 3t. So let's read this off again. So I have L of t squared e to the 3t is equal to 2e to the 3t. Now what is it that I'm trying to do here? What I'm trying to do is use this to find my particular solution. So let's go back to my third step here in this process. So find a linear combination of the resulting d plus 1 equations whose right-hand side has real part equal to f of t, and read off the particular solution. So again, d is 0, so this is a single equation I need. That's what I'm using here. The right-hand side, I want the right-hand side to have real part equal to f of t. My f of t was 4e to the 3t. Okay. Now, if I want this right-hand side to be 4e to the 3t, what do I do? Well, I have 2e to the 3t. I just need to multiply by 2. What's nice is this L is assumed to be linear. That's kind of the point of this whole process. So if I multiply both sides by 2, I can move that 2 inside of L on the left-hand side. And so what I get here is this is L of 2 t squared e to the 3t is equal to 4e to the 3t. What is this telling you? This is telling you that if you apply L to the function 2t squared e to the 3t, what you get out of that is 4e to the 3t. But that's just saying that 2t squared e to the 3t is a particular solution to this equation. So what this is saying is that the particular solution is 2t squared e to the 3t. And so the general solution I seek is the homogeneous solution, c1 e to the 3t plus c2 t e to the 3t plus the particular solution that I've found using key identities. So that's plus 2t squared e to the 3t. And if you feel like it, you can quickly check that that actually works out. Okay, so what's a quick way of checking? If you believe that you found the correct homogeneous part, then applying L to this thing, the first two terms, applying L to that, you know you get 0. Because that's the homogeneous solution. L of that thing has to be 0. They solve the associated homogeneous solution, or the homogeneous equation. And then L of this thing, what we showed using the key identities, the L of 2t squared e to the 3t is 4 e to the 3t. So that's the deal. That's how this works. So that's how we did it. And you see, we found the homogeneous solution almost immediately, so the real work was in finding this. And unfortunately, this is about as easy as it gets. So almost every problem you do like this is going to be slightly more involved. But for practical concerns, we're not going to have you doing anything too crazy. Now that we've moved to online stuff, and I'm going to give you more time on the exam, I could ask you to do something a little, like, tiny bit crazier than I would have, asked you if you were having to take the exam in person, but it's not going to be anything too crazy. So let's go back to this list for a second. It's a nice, like, overall view of this, even though we don't know the specifics of exactly how to do all these problems that can arise like this. One thing to note is that D is really the thing that determines how many of these equations you're going to end up with, right? So the number of equations you end up with possibly having to use to help you figure this out is D plus 1. So in general, the larger the degree, the larger D is, the more annoying these problems are. Okay, so if you really want to try to practice some of these things, to get good at these things, then doing problems that have high degree is a good starting point, because those are by far the most annoying. Since, like I said, D determines how many equations you get, so kind of how annoying these are. So basically, if you understand how to set this stuff up, you're already in good shape. Then it's really understanding the algebra. And the trickiest bit of that comes from the complex bit. So before I move on and do any more examples, I'll check, see if anybody has any equations. Let's see here. Yeah, so the question was, why am I actually multiplying by 2? So I'm wanting it to match up with the right-hand side. So the last thing I said here. So basically, find a linear combination of the resulting D plus 1 equations such that the right-hand side has real part equal to f of t. I didn't have to mess around with talking about the real or imaginary part, because this particular problem, I didn't have to involve that at all. But so in this case, everything, I didn't have to worry about taking the real part, so I just was able to look at it. The whole point in the process of any of these problems like this is I want this thing that I end up with here on the right, I want that to match the right-hand side function I started with. Okay, so the right-hand side function I started with, I want all this to match, and so that's why I multiplied by 2 here. Okay, and I can do that. Scaling by a constant is something I can do. That is kind of the tricky bit. So, like, what algebra are you allowed to do here? You're allowed to scale by constants. The other stuff, you have to use the equations to. That's what I mean by linear combination, and that's the trickiest bit of this. So I'll do an example of something a little bit more involved here in a second. Let's see. Any other? Let's see here. Oh, m to m plus d. Again, the reason why you need those, you'll see when I do an example that has high degree of why you need more than one. It's because one of those equations is not going to give it to you. You have to combine the equations in some way. The multiplicity was found by solving. Yes, the multiplicity comes from the characteristic polynomial. So you don't know what the multiplicity. Like, if I just give you an f of t, So if I just give you an f of t, the only thing that you can write out is the degree and the characteristic. So if I give you a function, f of t is equal to blah, okay? Um, so if I give you just any random function you want to think of that is in characteristic form, and I say f of t is in characteristic form, list me these things. I can have you list the degree and the characteristic for any function in characteristic form. You don't need to refer to the equation at all. But if I ask you for the multiplicity, the function itself is not what matters. What matters is the function and the equation on the left. Yeah. So anyway, so that's how that goes. So yeah, you have to refer to the characteristic polynomial to answer questions about what the multiplicity is. Okay, so let's do one more example. So let's do an example that involves something else. Okay. So here's one that's not too bad. Okay. Yeah, all right. Okay. So let me Okay. All right. So here's an equation. Y double prime plus 2y prime plus 10y is equal to cosine 2t. So find general solution. Okay. So how do I find a general solution to this thing? Process is exactly the same as before. So general solution to such a problem is always in the form of the associated homogeneous solution plus particular solution. Okay, so first thing is to find homogeneous solution. So the associated homogeneous problem is y double prime plus 2y prime plus 10y is equal to 0. Okay, so characteristic polynomial, this thing, z squared plus 2z plus 10. Okay, so you could just use the quadratic formula if you like, or you can notice, hey, this is like z plus 1 squared plus 9, so z plus 1 squared plus 3 squared. And so you can immediately find that the roots of this thing is minus 1 plus or minus 3i. So roots z is minus 1 plus or minus 3i. Okay. All right, so that's a quick find here. So then what is the associated homogeneous solution? So remember the way that this goes is this is c sub 1 e to the minus t cosine 3t plus c sub 2 e to the minus t sine 3t. Okay. Oop, I'm off camera. Okay. Okay. So there's the homogeneous solution done, but most of the work is in finding the particular solution. So I need to write out those quantities that I mentioned last time. So my right-hand side is cosine 2t. A couple questions. What's its degree? Well, again, its degree is 0 because there's no polynomial term in t, right? So the only thing multiplying this is a constant 1, that's degree 0. So its degree is 0 still. The question is, what is its characteristic? So mu plus I nu. What is its characteristic? Remember, let me bring back my functioning characteristic form. This is what a functioning characteristic form looks like. Characteristic mu plus I nu is determined by what shows up here. This is e to the mu t cosine nu t. That term should show up. There's the e to the mu t sine of nu t. So looking here, what is going on here? Well, there is no e showing up. So this mu has to be 0. And in nu, there's a cosine of 2t. So nu needs to be 2. So this should be 2i. Okay, the online notes will write I2. It doesn't matter. So anyway, here's a question. So I get this kind of question a lot. There's a cosine of 2t here. And you might say, oh, well, if mu is 0, e to the 0t is 1. It makes sense. There's a cosine of 2t here. Nu is 2. But if mu is 0 and nu is 2, and e to the 0 is 1, shouldn't there be a sine of 2t term here? Well, the reason why we can interpret this as still having characteristic 2i is that we can just say all of these coefficients b are 0. And all of these a coefficients are 0 except a naught, which is 1. So that's this thing being in characteristic form, having degree 0, characteristic 2i. The way that characteristic form is defined, it's not ambiguous, meaning that there is no, I give you a function, there's not some way of interpreting it having a different, these quantities can't be different. These quantities always have to be the same for a given function. Okay, so then to answer what the multiplicity of this thing is, I have to look at this characteristic and ask myself, is this a root of the characteristic polynomial? Well, the characteristic polynomial has roots -1 plus or minus 3i. 2i is not one of those roots, and so its multiplicity is 0. Okay, so it's got multiplicity 0 and degree 0. So the only equation that I should need following my process is the key identity itself, like the first starting thing. So if I look at what the key identity is, this is L of e to the zt is p of z e to the zt. Okay. Okay. So going back to my key identity process, I look here and I say, so I was supposed to evaluate the m through m plus d, so that's 0 through 0th in this case, derived as the key identities at the characteristic by setting z equals, in this case, 2i. Okay, so this is, he's saying L of e to the 2it is equal to p of 2i e to the, oh, I didn't close that, e to the 2it. So this is a little strange. It's a little weird. Why is it a little weird? Well, it's a little weird because if you go ahead and look here, right, just ignoring what I've written here for a second, p of 2i, well, 2i is an imaginary number, right? 2i is a complex number. And I'm plugging 2i into this polynomial thing, and it's not a root of it, right? Yes, this polynomial has two complex roots, meaning I plug in these complex numbers and I get 0. But 2i is not one of them, so I plug in 2i here, and what do I get? Well, I just get like some random complex number. So this is like some complex thing, and that's a little strange here because nothing that I wrote up here in this equation has complex numbers showing up anywhere, right? So what do I do with that? Well, that's why in the description of this general process, I look at this and I say, find a linear combination of the resulting equations. In this case, it's just a single equation since d is 0, whose right-hand side has real part equal to f of t, and read off the particular solution. So how does this work? The idea here is that I notice that this equation I've written down is respected if I replace these quantities with the real part of these quantities instead. So what does the real part mean? So if you have a complex number, so you have a complex number a plus or minus bi. Okay, so a and b are real numbers, and a plus minus bi, that's a complex number. I is the complex unit, right? There's a couple of operations I can talk about on a complex number like this. There's taking the real part of it and taking the imaginary part. So taking the real part of this, what is the real part of a complex number like this? It's just a. Okay, and maybe I don't want ambiguity here, so I'm going to get rid of this minus. I'm just going to say this is a plus bi. Okay, so a plus bi, the real part of that is just a. The imaginary part of a plus bi is just b. So the real part of a plus bi is really just the real number that's in the real part. It's the thing that doesn't multiply I in this expression. The imaginary part is the real number that multiplies I, but it doesn't include I. Notice neither of them do. So the real part of an imaginary number is real, and the imaginary part of an imaginary number is also real. Both of those are real valued things. Okay. So what I mean by the real part is this equation is respected if I replace these things in this way. Okay. Okay. So here's the thing. So first of all, how do I compute this? I'm going a little bit over time, so what I might do is stop here at this point and continue on when I upload a lecture over the weekend. I'll start here and finish this example. So I'm going to stop here for now, and I'll upload a portion of this later over the weekend that finishes the rest of this. So I'll go through an example in this fashion. I'll work through a couple of examples with complex characteristic. And then I'll do a couple of more complicated examples using key identities. And then that'll basically finish it up. And I'll go ahead and do undetermined coefficients as well, since I told you when I first introduced this that I'm never going to require you to use one over the other. There's a couple of instances where key identities are a lot quicker than undetermined coefficients, but there's not a single problem that could be done with one and not the other. They're applicable in the exact same problem. So let me quickly go over example. Let me go over some questions here. So oh yeah, so someone was asking how did I use the linear combination in the example. In the example I did, there was only a single equation, so I didn't need to use a linear combination. That is actually the hardest thing that you can do with key identities, is be forced to use some linear combination. So so I'll do that. That'll be like some of the more advanced examples of the stuff that I do. Let's see. Are we ever required to answer a question using key identities, or are we allowed to use undetermined coefficients? So yeah, I just answered that. So no, you're not ever required to use one or the other. You can use either of them. Let's see here. Yeah, you always have a choice. Do you need to memorize different key identity equations? You don't necessarily have to memorize all of them. You should know Pascal's triangle, and you should know the pattern that they follow. So know the left-hand side and know like the first two lines. When I am referring to lines, I'm saying in this case. So you should know these two, and then know Pascal's triangle and how this pattern works. That's all you need to have memorized. How do we know which key identity equation to start with? The first one you use is the mth one. So for instance, in the example I did here, the reason I started with this one, and it was the only one I used, was because the multiplicity was 2. So in this example, the multiplicity was 2, so I started with this equation. If the multiplicity had been 0, degree had been 0, I would have started with the key identity, which is exactly what I did in this last example that I was doing. Okay. So let's see here. That's how we know which one to start with. So you start with the one that is the mth, so m being the multiplicity, and you go through m plus d. I haven't done a single example yet where you've had to use more than one equation, so don't get confused thinking that I've done something like that. What's the pattern? The pattern for key identities is one that the coefficients come from Pascal's triangle, and the other pattern is that they count down, right? So you have p of z e to the zt. So here you have t e to the zt, so you have p of z t e to the zt plus derivative of characteristic polynomial, and now there's no t. Okay, going to the next one, I have t squared e to the zt is the thing that L is being applied to. I get p of z t squared e to the zt plus 2 p prime z t e to the zt, so the power of t is reducing by 1 each term. And then lastly, p double prime z e to the zt. So if you know that counting down pattern plus the coefficients coming from Pascal's triangle, that's the full pattern. Multiplicity is the multiplicity of the characteristic as a root of the characteristic polynomial. And yeah, I mean, as someone else pointed out, technically you don't have to memorize anything since the exam is open note. You can use the online notes for the exam. So there's in a sense you don't have to have anything memorized. But yes, if you were doing this blind without reference to anything, you would need to have it memorized. Yeah. Okay. Yeah, typically these lectures will be like an hour long. I know that this one, the lecture portion of this one is technically shorter because I was talking about a bunch of admin stuff. So I'm going to make a bunch more posts and updates to syllabus and post some. I'm going to record some stuff over the weekend. So yeah, I used 2i because 2i was the characteristic of the right-hand side. So 2i is characteristic of the right-hand side, whereas the roots of the characteristic polynomial of the associated homogeneous problem was, like you said, -1 plus -3i. So yeah, there's two different mu plus I nus showing up. That's why in the notes for the roots of the characteristic polynomial, if they're complex, the notes uses r plus minus is, and then mu plus minus I nu for the characteristic. I use mu plus minus I nu for both of those, so maybe my way of doing it's a little bit more confusing. I think the online notes used to do the same thing that I did, and then I guess that he probably also got complaints over that. Yep. Okay. So that's. Are we still covering all the original material? No. There's some things that'll be gotten rid of. So the largest portion of what's gotten rid of is going to be from chapter 3. So nothing, as far as the material goes, nothing will really be changed very much at all until we get to chapter 3. So some stuff will be shaved off of chapter 3. But no, I will record, if I feel like there's some extra bit of stuff that I want you guys to know, I'll record some stuff. But like I said, I'm not gonna record like a pile of lectures and then say, okay, now you have to, like do an exam on those like pile of lectures that I haven't answered any questions on. So I think that's pretty much everything. So I'm going to end the stream now, like I said. So this should be available pretty much immediately. If not immediately, then give it a couple hours. It'll be available at this account. I'm gonna have most of the streams public. We'll see. I might have someone do some moderating next time to keep the spammers out. But it should be public, so at the time of lecture, you can just go ahead and head on over, like 5 to 10 minutes before, and join. I should have it up and running. If not, for at least the first couple weeks, I will post a link in the announcements just to make sure everybody knows what's up. Um, the cats. Well, I'll hold on. I will find one. Oh, here's a cat. This is the best one I have to offer. This is definitely a premium cat. Anyway, so yeah, so like I said, I'll keep you all updated with everything that's going on, and whatever happens, you're not going to bear the brunt of it. It will, it will be smoothed out. You guys, your burden won't be increased. In fact, you should like this. I think that it will make your workload lighter than it would have been were it not for this interruption. So anyway, so that's the general philosophy I'm going for. But anyway, I'm gonna end the stream now, and I will record something over the weekend and post it, and I'll let you guys know when I do. So anyway, all right, I'll see you guys next week.